Professor Hill, and now we are going to finish up water and ocean structure today. We are going to focus on, last time we ended up with different water masses that stratified the ocean due to different densities. Now we're going to go sort of backwards in a way, and we're going to talk about three major layers that aren't part of this, these separate masses. Three major layers in the ocean structure, and we're going to talk about where certain things like temperature and salinity and pressure change the most, and how they affect the way light and sound travel in the ocean. All right, so again, apart from those major water masses like the Antarctic bottom and stuff like that I was talking about last time, the overall ocean is structured by density, right? Makes sense. The lightest stuff's going to be at the top, the heaviest stuff's going to be at the bottom. Overall, we call the surface layer the surface or mixed layer. What would it be mixed with, do you think? The atmosphere. You know, that's where the oxygen and nitrogen and the gases can be interchanged. This is the smallest part of the ocean. It only takes up about 2% of the total volume, but it's very, very important because that's where most of the food chain begins. It varies, as you can see from this. Let's look at this diagram here. So right here is 0 degrees latitude, so that's the equator, right? And we go down to the Antarctic Circle, and we go up to the Arctic Circle. It's showing you, these colors are showing you that the mixed layer is thinnest at the equator. It gets thicker, you know, midway up the globe and midway down the globe, and it's completely absent in the Arctic Oceans and the Antarctic Oceans. Then we have a second layer that takes up about 18% of the total ocean, called the pycnocline. The pycnocline is a very interesting place where temperature and salinity and pressure can change very rapidly. Again, you see it's not evenly distributed. Its thickness can vary. About 40 degrees north and south of the equator is where it's the thickest. And again, the pycnocline appears to be absent at the poles. Last but not least is the deepest water, what we call the deep layer, even though it's at the surface as you get closer and closer to the Antarctic and Arctic Circle. But it's generally below 3,300 feet, and it makes up the most mass of the ocean, about 80% of it. I have been taking out these, a lot of my slides that I do when I have an in-person class, because we have multiple choice questions that count for part of your grade. But I've decided to start leaving some of those in so that you can use them to review your own knowledge as you go through these. Now, of course, this should be an easy question that you shouldn't have much problem answering. Which of these three layers is going to be the least dense? The one floating on top, right? The mixed layer. And how do you explain the poles? Why don't they have a surface and a pycnocline? Well, keep that question in mind, because you probably can't answer it yet. You don't know that much about the layers. So keep that question in mind. That's the kind of question that, you know, it could show up on a test in some form or another. But if you have it in mind, you know what you're looking for as I talk. Okay, we're going to talk about the surface layer a lot more through the semester because it's so very important to us on this planet as life forms on this planet. It moderates global temperature. That's a biggie, right? And it's the primary zone of organic productivity on this planet. Okay, those are two big things. It moderates climate, it produces food. But we'll get into it in more detail later. We're going to talk today more about the pycnocline layer, that more middle layer, and that's because that's where the sharp changes in temperature and density and pressure happen. Now these pictures, some of these are in your book, so you know, you don't have to write them down or anything like that. They're in your book. They're really good pictures. So we got our three different layers here. So we're in the pycnocline. So what we're seeing here, they're trying to show you that this white layer up here is the surface. And this dark layer down here is the deep layer. So the mixed surface, the deep layer. We're interested in this pycnocline. And what we've got here is a column of water that's supposed to show us the temperature, one that's supposed to show us the change in salinity, how much salt there is, and the one that shows us where the change comes in density. And like I said before, there is a change in density, but you can only compact water so much, right? Okay, so let's go with temperature. In the pycnocline, what happens to the temperature? You have low here and high here. So we're at the surface. They're just sort of randomly making this the surface temperature. And you would expect, as you go deeper in the ocean, for the temperature to drop off, right? It's going to be colder down there because the sunlight doesn't get down there. As long as you understand how things work, you don't have to memorize the answers, right? You don't have to say, what does temperature do with depth? I memorized this. No, you just use common sense sometimes, you know. You say, there's no light down there. It's going to get colder. And where it gets colder the fastest is at the thermocline. It is the layer of the pycnocline where the temperature, the temperature, changes rapidly. And if you do much swimming, or if you've ever done scuba diving, you will notice that layer when you're going down, because all of a sudden suddenly you're like, okay, I'm cold, unless you're wearing a wetsuit. All right, salinity. How much salt's in the ocean? Again, they just picked sort of an area. We know that salinity varies, right, between 33 PSUs to 37 PSUs average. So they picked one. And during, when you go through the halocline, because halite is salt, when you go through the halocline, the salinity increases. Again, now you could memorize that, but how could you remember that without memorizing it? Well, think of where does it rain? It rains on the surface, and rain mixes with the seawater and makes it less salty. Also, the rivers drain into the ocean. So the surface is going to be a little less, it's more likely to be less saline than the deep area. Okay, so salinity goes up at the halocline. Density. All right, density. How much can we compact water? Well, you figure that obviously the deeper you go, the more miles of water you have on top of you, the more pressure you have. So it's going to become more compact, more dense. So again, you don't have to memorize these if you can just remember how to think, right? So at the pycnocline, that's where the temperature, the density increases. All right. Okay. Oh, didn't know I did all that. All right, these are some of the questions, you know, you can just look and see if you know the answers to. All right, now, just to make sure we are all on the same page, we've got our North Pole and we have our South Pole. 66.5 degrees north and 66.5 degrees south. That's the Antarctic Circle and the Arctic Circle. Once you go above or below 66.5 degrees, you're getting into areas where sometimes they don't get any light from the sun for 6 months a year. So that's why they're important. The Tropic of Cancer and the Tropic of Capricorn at 23.5 degrees above and below the equator. Those are significant in that they are the two places in the world where the sun can go directly overhead. They can anywhere actually between these two. So that's what their significance is. Now, the reason I'm telling you about these is because we sometimes talk about the polar zones, which will be the zones above and below 66.5 degrees, above and below the Arctic and Antarctic Circle. The temperate zones, which are between the tropic zones and the Arctic circles. They're kind of temperate. They're kind of warm, not too hot, not too cold, right? And the tropics are between 23.5 degrees north and 23.5 degrees south. So that's the coldest part of our planet. So in general, and of course this is very generalized, and it doesn't have these perfect layers like this because we have mountains and continents and all sorts of other things going on here. But these are the general layers, so that when I talk about the temperate zone or the polar zone or the tropical zone, I want you to understand this is what I'm talking about. Okay. So that brings us to this really neat diagram. So what is this diagram telling us? That's the first thing we got to look for. Well, on the top and the bottom, we see we've got temperature. Temperature in degrees Celsius, temperature, blah, 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 temperature in degrees Fahrenheit. Okay, that's good. And on the left and the right, we have depth. Depth in meters and depth in feet. Then, in the middle here, let me see if I go on to the next one. Yeah. In the middle here, we've got 3 lines. We have the polar, which is blue, the temperate, which is green, and the tropical, which is red. And so what we're trying to do is find, obviously, temperature with depth. We notice that all 3 lines come together when the water gets deep. They all have about 4 degrees Celsius, which is close to freezing, but above freezing in Fahrenheit. So basically, once you get down below 1,250 meters approximately, or a little more than 4,000 feet, it's cold. It's really cold. It's just above freezing. But at the surface, if you're in the polar area, it's still cold. It doesn't get much warmer, right? It stays, the water is just barely above freezing. Why? Because there's lots of ice there, and they don't get sunlight 6 months a year. In the tropical zone, it can get nice and warm in the summertime. And that's the warmest you're going to get on the planet. And it drops down very quickly as you go down through the thermocline, right? Until it reaches, 1,000 meters, and it joins up with the rest of the group. And then we have the temperate zone. Not so hot as the tropics, not so cold as the polar zone, kind of in betweenish. And again, it drops down really fast as it goes through the thermocline, and then kind of parallels the tropical until they all meet up. All right. So then, I shouldn't have had this question up here to distract you while I was talking. Maybe I should take that out until later. But this is just, again, one of those questions you can use too. If they're in yellow, they're those questions you can use to test yourself. All right, the deep zone, what about it? Well, it's deep. As I was saying, it's not very much above freezing. They have their temperatures here, 30.5 to 37.5 Fahrenheit, which is -1 to +3 in Celsius. There's very little energy down there because it's very cold. There is stuff going on down there, but we'll cover the surface and the deep ocean much later. Right now, the pycnocline is really what we're interested in. When that temperature and salinity and pressure are changing, because they affect light and sound in the ocean. Who cares about light and sound in the ocean? Well, the other things that live in the ocean. Not everything lives above the land, right? So sound waves and light waves are both waves. They're like, waves have lots of similar properties. They're all moving energy, even though some of them are actually physical, like water waves, but they're always moving energy. Waves in the ocean, and we're talking about sound, or did I put that in there? No, it doesn't matter. Sound or light can, because they're waves, they can all be affected by these 3 things: refraction, scattering, and absorption. And I'll try to explain how and what those 3 things are. Refraction is the big thing we're kind of interested in right now. Refraction is how we bend a wave as it reaches a new layer that has a different density than the layer it's already in. So light can be traveling through, I'll show you an example in just a minute. Okay, I'll just show you. Here's the example. All right, so this is a light wave. Now this is above the water, but the same thing would work in the water. All right, so white light, the light we come from the sun, is made up of the colors of the rainbow, but they're moving very fast, and the differences between them are very small, and we normally can't see them, okay? But when white light hits something of a different density, so in this case, the white light is coming in from the left, and it's hitting that prism. The prism is made of glass, Well, glass has a great deal more density than air, okay? So it refracts the waves because the red and the yellow and the green and the blue are actually all slightly different. They are bent slightly differently. And so it separates them out into the colors of the rainbow. And then as it goes through the prism and comes out the other side, and now it's coming through the air again, it bends them again because now the density has gone down. Same thing would happen if it was underwater, if that prism was underwater, because water is not as dense as solid glass. So it would also bend it, not as much as it would with air because there's a bigger difference in density between solid and gas than there is between liquid and solid. But it would still be the same principle. It's all about density. You so know that density is going to be on the first test, right? You keep talking about it almost every class. That says the same thing. This is an example that you've seen, you know, if you put a soda in a glass, right? Or a pencil in a glass. If you they should have put a soda, not too many people put their pencils in a glass. But we know that the pencil is straight, but it doesn't look straight to us. Why? Because the light is coming through the glass and it's coming through the water, which is a different density than the air that it has to travel. So this light is traveling to our eyes, first through the water, and then it hits the air, and it's a different density, so it bends it. And so then it travels to our eyes and finishes traveling to our eyes. So we look down and it looks bent, but we know it isn't. Anyway, that's an example of refraction. This also happens if you happen to be a fisherman, especially if you're a spear fisherman. The fish or the object that you're after is not actually where you think it is because of that refraction. So I assume that spear fishermen learn to adjust for that. But a lot of spear fishermen actually fish completely underwater. Let's see now. Refraction in the oceans caused by changing density. Yes, I know that. Scattering. So we've done refraction. Change in the wave motion of either light or sound due to change in density. Scattering. Scattering is what happens when when a wave hits a molecule. And it scatters it, just like it sounds like, and just like that picture looks like. It bounces the waves off in different directions. All right, so this is a picture of light coming into the ocean. Now, instead of showing you white light going into the ocean, they're showing you all the different constituents of white light going into the ocean, the red and the orange and the yellow and the green and the blue and the purple. And what they're showing you is that the size of water molecules make it so that the blue and the purple and the green somewhat hit them and are scattered. Red waves, are they smaller or larger? I think they're larger. Anyway, because they're a different size, they do not hit the water waves as much and they are not as scattered. So that's why the ocean looks the color it does to us, because these water molecules are scattering the blue and the green light, and purple too, so that we end up seeing them that way. To look that up though, I think that it scatters green, and it's showing that it isn't. More on that next class. All right, absorption. So we've done refraction, scattering, absorption. Absorption, what's that mean? Well, this is kind of when waves of light or of sound, we're talking mostly about light right now, we're focused on sound in a minute, when they hit a molecule of water, for example, and their energy is absorbed into the molecule of water. And what does that do? When it takes in the energy, absorbs it, it warms it up. Okay? Warming of the ocean is actually a big environmental concern. The ocean is warming. It's been warming for quite a while, mostly because of anthropogenic activity, meaning human-caused activity, of us burning fossil fuels. But we'll get into all that later. So anyway, it translates into heat energy when it absorbs that energy. Let me see if this what this does. Okay, can't find that. All right, that's okay. Oh, I bet I know what that is. Okay, now let's talk about absorption. This is different than scattering. Okay, when it absorbs, it sucks it up. Okay, it sucks in the wavelength, and it gives the water more energy and warms it up. You can see that the reds and the yellows and the orange get absorbed very quickly as you go down. You know, we're doing meters here, right? So 300 meters is like 330 feet. Okay, you can see way up in the surface, the red and the orange and the yellow are absorbed. So that's how the sunlight warms the ocean. You see that the blue and the green and the purple go down much, much further. So if you actually look at things that are further down in the ocean, they do tend to look blue or green, whether they are or not. Another important thing about all this absorption is the photic zone, which we haven't talked much about yet and probably won't be on the first test unless I talk about it more, but let's just throw it in. The photic zone is where sunlight is used by little plants, mostly microscopic plants, in the ocean to produce food. That's different than the aphobic zone, which is the part of the ocean which is in complete darkness. So you see that even the blue light doesn't make it down past about 280 meters. It'd be like close to 700 feet, something like that. Okay, so I've been talking about refraction, absorption, and scattering. Good thing that wasn't a test. With light waves. Sound waves do the same thing because they're waves, all right? The average speed of sound underwater is very fast. It's much faster than it is in the air. Why? Because the waves that move through compression, and the molecules in the air are much further apart. So we've got these little eardrums. You've probably heard of them. They vibrate when they get these compressional waves hit them through the air, and then we hear things. If you go down, if you're a swimmer and you've ever swam in a lake where there's been like motorboats or things going on, you can hear really well underwater. You can hear every boat in the lake usually because the molecules of water are very close together, so the compressional waves are able to move very quickly because they can just touch the next thing they're being sent through. I don't think I'd ever ask you exactly how fast water moves underground, under the ocean. I'm not really interested in you memorizing lots of numbers. I'm interested in you understanding how the ocean works. So I would expect you to know it moves faster. Would I ask you if it moves 5 times faster? I sort of doubt it. All right, now this is important. The speed of sound underwater goes faster when there's an increase in pressure, which that makes sense, right? Because the molecules are closer together if there's more pressure. With more temperature, well, I don't know how to explain why that would be except that warmer things are vibrating at a higher energy than cooler things. So anyway, it says, I put in a little aside there, that for every 1.8 degrees Fahrenheit you go up, so a little less than 2 degrees, the sound travels about 15 feet per second faster. Again, I won't ask you some detailed question like that on the test, but I would want you to know that the warmer the water is, the faster the sound goes. Salinity also, all 3 of them, pressure, temperature, and salinity, make sound move faster. Salinity is not as big an effect. Let's see what I want to continue recording. I want to see what this thing is that I have here. Usually there's all sorts of neat things I can show you. Let's see if this is a neat thing. I don't want to sign up for anything. Oh, it's an error. Why did it give me an error? What a shame. All right, I will just destroy that then because I'm not interested in playing around. and having to not what I'm trying to do. Let's get this back to the full size. All right. Okay. Here's another graph. Love these graphs. Graphs are going to be on the test, okay? So that I know you know what you're talking about. So what do we got on the y-axis there? The speed of sound. All right, it's moving slower here and faster here in meters per second, not feet per second. Temperature. So what are we looking at here? How fast sound moves with respect to increased temperature. But we got 4 different lines. So we have something else going on here. What is it? PPT, this is parts per trillion. They should have put PSUs, right, for practical salinity units, but they didn't. PPT is a different unit. That's not going to be on test. But you can tell that the blue is bigger than the other blue, which is a dumb thing to do. They could have put it yellow, but anyway. So what we're seeing here is a bunch of different things. First of all, we're seeing that no matter what the salinity, the warmer the water, the faster the sound. And if it's more saline, because this is the most saline, then less, then less, then less. You can see the more saline it is, it also moves faster. Again, it's not as big a difference, but it's appreciable. Another great graph that's in your book. So we're looking at sound in meters per second. So velocity, sound velocity, how fast it's moving in meters per second. Slower, faster. Then we're looking at depth in feet and depth in meters. And let's just go to the feet, right? 0 feet to 1,200 feet. So there's about 5,600 or 5,800 feet in a mile, something like that. So this is about 2.5 miles, something like that, okay? 2.5 to 3 miles. So, okay, surface, 2.5 to 3 miles. We can see that the sound is moving much faster at the surface. Okay, we know that sound is affected by temperature, by salinity, and by pressure. What is affecting the surface the most? Well, what do you think? When you're to the surface, it's going to be the warmest from the sun heating it up through absorption. So that's probably what's making it go so fast. And then we're going through the pycnocline. Things are changing. Now we got a minimum sound quality down here at about 1,000 or about 3,000 feet below the sea level, and then it gets higher as you go down again, right? And why would it get so high down there? It's not the temperature, because it's cold, right? But we know that it's more saline down there and much more pressure. So, all right, so yeah. So again, when you're looking at these, try and use the different variables, temperature, pressure, salinity, that might make the difference. Now this minimum sound thing is, and if you can't remember your different pycnoclines, right? Because we know that the pycnocline is like between, okay, we'll do it in meters or feet. Let's do meters because it's easier. 200 meters to 1,000 meters is the pycnocline. So from about here to here is where the temperature, the temperature is dropping, the salinity is going up, and the pressure is going up. So it's obviously, this drop is definitely from the temperature. But you should be able to take these diagrams and use them to help you understand these other ones. That's what this whole thing's about, is getting all this knowledge so that it's like little working pieces that you can figure things out with and not just memorize stuff. Most people know that animals take advantage of the speed of sound and the quality of sound in the ocean to hunt, some of them, called echolocation. It's like sonar. The porpoises bounce sound waves off of their prey, and that tells them where they are. Because, of course, light isn't that great down there, so they might not be able to see them that well. I think I already said this. Sound waves are also subject to refraction, scattering, and absorption. Now, I want to talk about why we have a minimum sound quality at what we call the SOFAR zone. This is called a special name because it is the minimum sound quality. We know that because it's still in the pycnocline, that salinity, temperature, and pressure are changing. And this is about the bottom of it. So we're going from the pycnocline into the deep water pretty soon. And temperature, you can see that the density, you see that the sound velocity is going up. The reason it's going up is the density is going up now, right? So what I'm trying to tell you here is that this water down here is becoming more dense than this water up here. And what happened with light when it had to move through something that was more or less dense than the next thing, you know, when it was traveling through air to glass or whatever, or glass to air, when the density changes, it refracts, okay? And that's kind of what happens here. This is in your book. It's a little bit complicated looking. This over here on the left is just showing you that little layer, and this is showing you the SOFAR zone. It's an area where sound can get trapped. It bounces from the top of the SOFAR zone to the bottom and back up. It sort of bends and refracts the sound waves that are moving through it, partially because of the difference in density. Now, what's so important about that? What it means is that at this particular depth in the ocean, where sound is moving as slow as it can move very, very far. It can move thousands of miles. There are animals that care about that. What kind of animals care about that? Whales care about that, right? They make all those really cool whale songs, and that's their favorite zone. I think it was baleen whales I read. Like it a lot. No, continue recording. Are particularly fond of it. Control-C. So just because they're cool, I thought I would show you. There's a, in case you're interested at all, this is a whale sounds lab, right? And this guy's doing work on whale sounds. And down here, we have bunches of different whales, right? We got humpback mating songs. We have sounds for hunting. Let's just hear a humpback mating song for a minute. I don't know if that's a male humpback or not. I assume it is. If you're a female humpback, that would sound really awesome to you. It actually sounds awesome even if you're a person, right? And then we got this other one. You know, they have actually, I looked on the internet, I guess some people find whale songs so soothing that they have hours of them. People sleep to them. I don't know if I'd want to sleep to whale songs, but this is just kind of neat. It's a really short little 40-second video. We got some blue whales. Now, obviously, those guys are way far above the SOFAR zone, but it's harder to get light, and well, it's harder to get down there and film them when they're in the SOFAR zone, right? Okay, let me get this back on track and hope it's still recording. I would be so irritated if it stopped recording. Okay. This is an aside, sort of a relevance thing. Why do we care? I mean, you could just care because it's cool to know how the planet works, right? But this is also working into climate change because This is the Arctic Ocean here. We're looking at the planet from the top. We got Greenland, America, and Alaska. We've got Eurasia here. Here's Norway and Sweden and Finland. And this area here has traditionally been locked in ice most of the year. And it's a place where creatures like the narwhal live. And global warming is causing these areas to not be landlocked or ice locked anymore. And because of that, it's opened up shipping lanes, not just tourists, but now where a lot of countries have set down their flags literally sometimes on the bottom of the ocean saying we're going to, start mining for oil here because it's feasible now. So anyway, the reason what this has to do with sound is that the addition of all the human activity, the ships and the drilling and creating drilling platforms and all that is they believe it's very disruptive to the life up there because it disrupts their communication with each other. All right, back to the pure science part. There is another thing where it's called the shadow zone, I believe, and this where the sound waves are deflected or reflected or refracted in reverse. They reverse away from a certain area. Now, where is that? A maximum sound velocity, I believe. They said about 260 feet below the surface. There is a high velocity zone that works to deflect sound, all right? And so the relevance of that, if you're interested in things like war, is that if you're sneaking up on someone with a submarine, that's the zone to stay into to make sure that the ships above can't hear you coming. Okay. All right, you got any questions? Email or talk to me.